So, continuing our discussion on the diffraction gratings, here I am showing a slightly improved figure. You can see the different ridges here. Okay. So, there is this is known as grating normal, that is it cuts the grating vertically. Okay. This line is grating normal and incident radiation comes like this, and it will go a hit there and comes out at different wavelengths. Okay. So, this is the degree incident angle, and the all radiations will be coming out like this. I have shown here the different wavelengths. This is 300, 500, 700, 900, 1100. That means, if I rotate this grating from vertical position slowly like this, first I can get 300 nanometers and then 500 nanometers if I rotate it more, and then slightly more rotation. If I change this angle, I will get 700, then 900, 1100. That means, right from 300 to 1100 nanometers I can get by rotating the grating. Okay. So, the different I will when I get 300 nanometers, okay, I also get certain amount of radiation corresponding to 150 and 150 nanometers, that is wavelength, half of the wavelength. Then I can get still lower, around 60 or something like that. So, these are known as, this is known as first order, this is known as second order, this is third order, like that different wavelengths I get. The first one what I get is 0 order. Here it is here 0 order. I have plotted here, that is it covers from 250 to 200 to 1100, okay, 200 to 800 here, 0 order. So, I get 0 order, first order, second order, etc., etc. And then this is second order, this is third order, 0 order, like that I will get different. But the intensity of the second order would be much less than the first order. It may be less than 50% or something like that. Intensity of the third order also would be much less. So, if I want or not, at any angle I get both orders, both or 2 or 3 orders with different intensities, may not be significant, but for very accurate work I cannot take as the first order straight away, because there will be certain amount of radiation associated with the second order, that is half of the wavelength. So, if I want to use only a very accurate work, some people use two gratings. Some people use 2 gratings. With the first grating they get the first order and then second order also, and that radiation that comes out of that, they will make it fall on the another grating, and again they get the first order. So, at that time the intensity of the second order would be almost 1/3 or 1/4, like that. There are ways of getting rid of the second order, third order, but quite often it is not very important for routine analytical purposes. So, one grating should be more than enough for typical applications. Okay. So, this is how sometimes people use a grating known as Echelle grating. Here I have to tell you that the number of rulings is what makes the quality of a grating. Typical rulings vary from 1200 to 30,000 rulings per centimeter. It is a great achievement, it is an engineering material, it is great achievement to draw 30,000 lines, depressions per centimeter, and the maximum typical numbers used in spectrophotometer contain from 1200 to 1800 or something like that, either 1200 lines or 1800 lines. That means, in a single grating you will get about 1200 prisms. So, the accuracy of the wavelength that comes out would be much more of very high quality compared to a prism, because in prism there is only one prism. Here I have 1200 prisms for the same radiation. So, a typical wedge looks like this. In this figure I have shown here now, 30-degree prism is like this. So, if I have to use a diffractometer, I should use one with very high numbers, but there is a special case. I want you to understand that I can use smaller number of gratings containing about 70 to 80 grooves per centimeter, and then I can use a prism to separate the remaining this thing. So, here what happens is the second order, third order gratings are automatically removed with minimum effort. So, instead of using 2 gratings, I can use only 1 grating and a prism. This type of arrangement, where the number of rulings are hardly 75 to 100, 130 etc., that is known as Echelle grating. So, I have shown you in this figure the Echelle grating is here, okay, and then I make the radiation fall here, take it through this, and then I get the diffraction orders here. So, the wavelengths lambda 1, lambda 2, lambda 3 I am getting in this area, and this is a beautiful way of making a simple. Nowadays 90% of the instruments in infrared spectrometer, they do contain Echelle gratings. Now, I want you to look at the top figure. Here I have a concave mirror, and then all the radiation that comes out is all parallel. That is the quality of the concave mirror. That is why a lot of concave mirrors are used in most of the instruments. And then I put a mechanical plate here with a small hole. That allows me to take out only a small portion of the incident radiation that is coming out and into the disperser. This disperser could be either a prism or a grating or Echelle grating with a prism and all that. Okay. So, from here I get all different wavelengths, and then I put one more slit here, okay, to choose the radiation that is coming out like this, either, or like here I can put a slit, or either change the disperser, get different wavelengths, or move the slit itself up and down. That is also possible. So, if I move down I get shorter wavelengths, if I move up I get the longer wavelengths. Now, you can remove the photo. So, there are different ways of doing this. Instead of a concave mirror I can use a plane mirror, and then mechanical slit, and then disperser, and I can have number of slits here. Instead of a single hole like this on the top, I can have number of holes which will permit me to take out different wavelengths simultaneously, both shorter wavelength and longer wavelengths. So, if I put a detector at each point, I will have what is known as multi-channel detector instrument. A very simple arrangement, but such instruments are also available, including the infrared spectrometers. Okay. So, the monochromator slits play an important role in determining its performance characteristics and quality. Usually 2 slits are employed, one as entrance slit, which I have shown you earlier after the concave mirror, and another one serves as the light source, and another one as the exit slit on which the image of the entrance slit is formed. These are all very standard stuff described in most of the reference books which I have prescribed for this course also. Okay. So, if the radiation source consists of discrete wavelengths, a series of rectangular images appears on the exit plane, which appear as bright lines corresponding to different wavelengths, that is all understood. So, movement of the monochromator setting in one direction or the other produces a continuous decrease in the emitted intensity when the entrance slit image has formed is moved at a distance equal to that of its full width. So, illumination of the exit slit with the desired wavelength is invariably associated with some unwanted radiation, and this unwanted radiation normally is a radiation having slightly differing wavelength than what we have chosen. So, whenever we use a particular wavelength from a monochromator slit, I do not get a single monochromatic radiation, but a band of radiation containing mainly the one what you have chosen plus a little bit of this side and that side. So, that is known as bandwidth. Okay. So, this is the pictorial representation of a bandwidth. So, here what I want to show you is at lambda 2 is my desired wavelength. Okay. So, the maximum intensity, this is the radiant power, and this would be the intensity on the y axis, and maximum radiation is here. But I also get a radiation corresponding to lambda 1 and lambda 3. These are also nearby, but maximum intensity lambda 1 is almost nil. Here at this point, this is another slit, okay, from here. So, at this point at the edge lambda 1 is nil, lambda 3 is nil, only lambda 2, but somewhere around this I get both lambda 1, lambda 2 and lambda 3, and the lambda 2 intensity would be very high. So, since I get all the 3 wavelengths corresponding to this radiation, that is known as effective bandwidth. Okay, this is my exit slit. So, so much of radiation keeps on coming, but it will correspond to a little bit of lambda 1 and lambda 2, and the effective bandwidth is described by the size of the exit slit also. Okay. So, that is what exactly I have written here. When the monochromatic light falls on the photocathode, that is a cathode with coated with alkali metals, electrons of varying kinetic energies are emitted from its surface and fly over to the anode in a phototube. As long as the voltage V is applied between the voltage and cathode is positive, it produces a small current. Now, we are talking about the interaction of electromagnetic radiation with detector. Okay, detector is nothing but a piece of metal on which alkali metals are coated. So, then what happens, when the radiation impinges on this, electrons of varying kinetic energies are emitted and a small current flows in the circuit. So, when the voltage across the phototube is adjusted such that anode is negative, the photoelectrons are repelled by the anode and the photocurrent decreases. That means, depending upon the voltage, I get different kinds of current corresponding to the number of electrons that are released whenever the radiation falls on the detector. When I do not have the sample, maximum current. When I have the sample, part of it is absorbed. So, the remaining part of the radiation that falls on the detector, that will produce less current. So, this current difference can be correlated to the concentration of the pollutant, whatever we are trying to determine. So, coming back to this, the photoelectric current is measured as a function of the applied voltage V 0 at which photoelectric current reaches 0, and that is multiplied by, we can multiply the electronic charge by the coulombs, 1.60 into 10 raised to minus 19, that gives the kinetic energy of the energetic electrons in joules. So, maximum kinetic energy for various coatings are plotted as a function of radiation frequency, and we get straight line response. We should get a straight line response with a slope of h with an intercept w, which is known as work function. This is all the theory of the detectors. Okay. So, the plots can be described by the equation Kem is equal to h mu minus work function w. W is the work function. So, the E is nothing but Kem plus W energy, that is corresponds to Hc by lambda. So, W is the characteristic of the surface material and represents the minimum energy of binding the electron to the metal atom. So, the moment binding energy is excess, equivalent excess of the binding energy, electron will be released and current will flow. So, it is equal to it is also equal to the energy of the electromagnetic radiation, that is energy of the photon, electromagnetic radiation required to eject the photoelectron from the irradiated surface. Okay. So, it can be concluded that no electron can be ejected until the work function is exceeded. Okay, that is k dot into e to the Em. So, the energy is not uniformly distributed over the beam front, but concentrated in packets or bundles of energy, which is a thumping confirmation of the quantum mechanical theory. That is all about the detectors. So, the equation permits the calculation of the energy of any electromagnetic radiation of known frequency or wavelength, that includes infrared spectroscopy also. Okay. Now, I will just arrange to give you a small demo regarding the energy of the electromagnetic radiation and how we can use it in our day to day life. I have given, I am going to present to you one small example. Here you can calculate the energy of the 5.5 angstrom unit radiation, that is an X-ray photon. So, here you can fill up the numbers, E is equal to h mu or Hc by lambda. Here you can put the h value, then C, this is 3 into 10 raised to 8, and then wavelength. So, if you solve this, you can calculate the energy of the incident radiation corresponding to this wavelength. Now, I can give you any wavelength and ask you to calculate what is the corresponding energy of the electromagnetic beam. So, that is the purpose of showing you this example. Okay. So, across the electromagnetic radiation, we can, if I know the wavelength, I can calculate the energy of the electromagnetic beam of that wavelength. Okay. Now, here is one more example, 430 nanometers. Earlier one was in X-ray. Now, I have in the visible region 430 nanometer. Again I use the same equation, E is equal to Hc by lambda. So, the numerator will remain the same, that is 6.63 into 10 raised to minus 34 joule seconds multiplied by velocity of the electron and divided by the wavelength, you get 10 raised to minus 19, that is 4.65. So, the energy is usually we express in kilojoules per mole. So, I can write 4.6255, I have to multiply it by number of the photons per mole, okay, into 10 raised to minus 3, convert it into kilojoules. You know, normally joules means we get lot of numbers. So, if I convert that, I get the energy of the 430 nanometer photon as corresponding to 278.4551 kilojoules per mole. This is only a demo example, but maybe I will ask you in the exam also. So, the quantum theory originally was proposed for black body radiation a little. Now, I want to explain to you quickly. other aspects of instrumentation, electromagnetic radiation, so that we can proceed on to the infrared spectroscopy part of it, that is the main body of our course, that we will proceed quickly. Now, I want to tell you that the quantum theory was originally proposed for black body radiation, that was extended to explain the emission and absorption processes. The essential postulates are like this: the ions, atoms and molecules only exist only in certain discrete energy states. So, when it changes its state, it absorbs or emits an amount of energy exactly equal to the energy difference between the two states. This is one postulate. Another one is, during transition, energy from one energy level to another energy level, the frequency or wavelength of the radiation emitted or absorbed is equal to the energy difference between the states. So, I can write E1 minus E2 is equal to h mu or hc by lambda, and where E1 is the energy of the higher state and E2 is the energy of the lower state. Now, I can also say for atoms and ions in the elemental state, the energy of the state arises from the movement of the electrons around the nucleus. This we have already discussed a little bit in the introduction part itself during atomic structure. So, such energy levels are called electronic energy levels. Then I have vibrational energy levels and rotational energy levels. So, the lowest energy state of an atom or a molecule that is at room temperature, that so the energy populated at room temperature is called as ground state. Higher energy states are termed as excited states. So, detectors used in infrared spectroscopy work on the principle of photoelectric effect, which I enumerated just now. So, these include photomultiplier tubes and diode array detector. These are the technical terms for the detectors used in infrared spectroscopy. So, we can continue our discussion on the interaction of radiation with matter. So, a sample can be subjected to a chemical stimuli in the form of heat, electrical energy or light, bombardment or chemical reaction. So, the stimulus causes the analyte species to move from one energy state to higher energy state. So, in the process, energy is absorbed or scattered. So, information about the analyte can be obtained by measuring the electromagnetic radiation. See, in most of the atomic spectroscopy, including infrared, molecular spectra and other things, the measurement basically is of electromagnetic radiation, not of the sample, but sample will have an effect on the energy of the electromagnetic radiation that it is going to interact with. So, most of the analytical equipment instruments measure the energy of the electromagnetic radiation. So, we can get the information about the analyte by obtaining electromagnetic radiation itself. Okay. So, this is how normally we depict the emission process. Here I have a sample, I supply energy, it goes from this state to higher energy state, and then this is E1, E2, E21 etc., different levels, and the energy difference between this and this is when there is no interaction, when there is interaction, when there is no interaction, like that at different wavelengths. So, that is emission. Now, absorption, here part of the energy is absorbed here, and what comes out would be the transmitted radiation, and its intensity would be lower than the incident radiation P naught. So, again I have similar energy levels 0, 1 and 2. I have E1 is equal to h mu 1, that is equal to hc by lambda 1. E2 is this, the difference between these two are represented as two peaks corresponding to those transitions. So, the emission of radiation is another one, but we are not going to consider much about the emission, because we are going to talk about infrared absorption spectrum. So, but just for the sake of brevity, let us spend a little time about the emission also. So, when excited atoms, ions or molecules return to the ground state, sometimes the excess energy is released as heat or in the form of radiation, that is photons. So, the excitation can be brought about by bombardment with electrons or other elementary particles that gives rise to X radiation. Okay. Now, electric current, a spark or heat source such as DC arc, furnace, etc., can be used as energy sources. This gives rise to ultraviolet, visible light, infrared radiation, etc. And a beam of electromagnetic radiation, this produces fluorescence sometimes. Exothermic chemical reaction produces chemiluminescence, but we are not going to consider any of this, but these are the different things you should be knowing about. So, there are different types of spectra. The typical spectra have three components, one is lines, bands and a continuum. So, line spectra are a series of well defined peaks, that is band spectrum consists of several groups of closely spaced but not well resolved peaks, and continuum part, as usual, it has no boundaries, it is just a sort of illuminated area, that is continuous spectra. So, by sometimes the line spectra and band spectra are superimposed on one another also. So, that is also seen especially in Fraunhofer lines in solar spectrum, but that is not important as far as our course on infrared is concerned. So, line spectrum of atomic particles are preferably obtained in the gas phase, especially in the gas phase we get line spectra, because the matrix effects are very less in the gas phase. So, typical widths of the peaks are of the order of about 10 raised to minus 5 nanometer or 10 raised to minus 4 angstrom units, and X-ray line spectra are produced by transitions of the electrons when they fall from higher energy level to the lower energy level. Okay. So, from higher shell to lower shell they emit certain radiation of lower energy, that is X-rays. Okay. And band spectra are produced by radicals, small molecules and bigger molecules also, but the peaks are associated with the vibrational energy levels. So, the lifetime of vibrational energy state is approximately 10 raised to 15 seconds minus 15 seconds compared with that of the electronic state excitation, that is about 10 raised to minus 8 seconds, almost double. The electronic state is almost half of vibrational energy state changes. So, the transition always occurs from the lowest vibrational energy level of the excited state to any of the vibrational energy level of the ground state. The loss of energy from vibrational levels to that of the ground floor and ground state lowest energy level occurs through the collision with other molecules. I hope you are able to understand what I am trying to tell you. Okay. Now, the first I take certain amount of material, excite it to higher energy state, and from there it falls slowly couple of steps until it reaches the ground level of the vibrational level of the excited state. It comes to 0 of the excited state and then it falls to the 0 of the ground state. So, that is what we are talking about. So, continuum spectra, there is a radiation from the black body when heated to incandescence, it produces continuum spectrum. I think everybody is familiar with this. So early morning sunlight containing red, blue, yellow, etc., it is all sort of continuum spectrum. So, the energy peaks shift to shorter wavelengths with increasing temperature, and heated solids are important sources of UV visible as well as infrared radiation. That means, the lamps which you use should be of heated solids only. Okay. So, what I wanted to tell you is the sources of the radiation for electromagnetic radiation are usually bulbs, which you are very familiar, Thomas Alva Edison's bulbs, tungsten lamps, etc. Nowadays there are LED lamps, this, that, etc., fluorescence, halogen lamps, so many types of, but all of them contain a heated surface. So, the most of the radiation sources are basically heated surface, even though they are called as bulbs technically. So, we will continue our discussion in the next class. Thank you very much.